Hello again. In this video we're going to discuss some basic equations and how to plot them in Maple in cylindrical coordinates though and in spherical coordinates. Alright, I'm going to show how to do that as a parametric description in cylindrical and spherical coordinates. But what we're going to look at is plotting some of the simplest equations. So if we're thinking about working in rectangular coordinates x, y, z, then the simplest equations are the constant equations, when like one of the variables is equal to a number, like if x is equal to 2, or if say y is equal 4, or z is equal 5, or whatever. All right, now in those cases what you end up with is planes parallel to the coordinate planes. So what we want to ask here is, what is it going to look like if we graph an equation like r equals a fixed number, like say r equals 4, or theta equals a fixed angle, like pi over 4, or z equals a fixed number, like say 5 again. Well, the last one, z equals 5, that's, since cylindrical coordinates are polar coordinates in x, y with z left unchanged, that's still going to be, as we're going to find out, a plane parallel to the xy plane. All right, and same thing with spherical coordinates. We're going to ask what do the graphs look like when you let rho be a fixed constant, like say rho equals 3, and same thing with theta. What if it's a fixed angle, like pi over 4? And what about phi? Same thing with phi. What if it's a fixed angle, like pi over 4, or pi over 6, or any other angle there? What's going to happen there? What are the graphs going to look like? All right, so we're going to go over and work on this in Maple. All right, I've got everything inputted here, so you can pause the video and take a look at the code on here, and I can post this file in Blackboard for us as well. But what I wanted to start out with is, okay, we do our usual thing where we load the plots package. When we want to make a graph of a 3D surface, a surface in 3 dimensions, and the one I'm going to be looking at initially here in these first two is the graph of this equation, z equals x squared plus y squared. In the previous video we converted that to cylindrical coordinates and spherical coordinates, but what we're going to look at doing here is the quote-unquote normal ways to plot those. All right, and that would be using the plot 3D command. All right, so you type in, just if you're using plot 3D or maybe implicit plot 3D, but when you're using plot 3D, you just put the expression involving the two variables in, and then you put your x and y ranges in. I chose the normal axes options. All right, and this one thing I want to pay attention to with this graph was we're going to see this 3-dimensional paraboloid, and Maple plots exactly what we tell it to. When we look down though, the z-axis at the surface, these trace lines on the surface are parallel to x, the x-axis and the y-axis. Okay, and the reason we see these corners in the graph is because Maple's plotting this whole square from -4 to 4 for x and -4 to 4 for y. So essentially it's taking that square in the xy plane and folding it up to create that graph. So that's one way to do the graph of an equation involving the variables x, y, and z, is if you have it solved for z, you can use the plot 3D command in Maple. Another way is using the implicit plot 3D command. Now, what's the difference between the two? When you're using implicit plot 3D, you need to type a whole equation in. So this is the command line version. This is the syntax of it. All right, typed, and you also have to type in an x range, a y range, and a z range. I chose this z range based on the previous picture up above because it's the same equation. All right, so I take the colon off and graph it. Here's what we're looking at. All right, you can see this. The picture's roughly the same. Implicit plot 3D makes Maple work a little bit harder though when we go to graph it. All right, and part of that reason is it's requiring Maple to use its solver feature on there, and to do that, Maple it takes just a little bit more work, and the graph just comes out a little bit rougher than it does using plot 3D. Or what I'm going to show you next is how to do a parametric surface in Maple. All right. Okay, so I paused the video for a moment, and I wanted to just type, just to save a little time with the typing. So what we're going to do here is show a parametric description. Notice each point on the graph of this surface, the graph of this equation, is of the form x, y, and z, but we know there's a relationship between z and the x and y components, whereas z is equal to x squared plus y squared. what that's showing us is that this ordered triple only depends on two parameters or two quantities, x and y. All right, and what we are going to see is we typically use the variables u and v. We don't have to for this. We could use x and y, but a lot of times you're going to see in textbooks u and v are standard for parametric surfaces. So we're going to just let x equal u, let v play the role of y, and then if you plug that in, since z is equal to x squared plus y squared, you're going to get z is equal to u squared plus v squared. And that's what we call a parameterization of the surface. So we've now rewritten each x, or each point on the graph in terms of two variables. To plot a parametric surface, it's very similar, except what we need to do is we need to make sure we have these square brackets around the ordered triple. All right, so we got to have those square brackets on there. And then afterwards, we put the parameter ranges, the u and the v range in. And then when we go to graph that, it's giving us essentially the same graph we saw using plot 3D and typing in just x squared plus y squared up above. But this will give us real good control when we go to talk about plotting the constant equations in cylindrical and spherical coordinates. So let's move on to do that now. All right, so what we're going to ask is, what is a parametric description, a parametric surface description in cylindrical coordinates when you fix one of the variables? All right, so what I'm saying here is look at this expression, look at our x, our y, and our z, and I'm going to fix r equal to 4. All right, so the first one's going to get, what we're going to look at is the equation, the plain and simple equation, r is equal to 4. Let me just jot that down in here. That's what we're graphing first. All right, now here's the syntax for it. All right, so again, plot 3D, we're doing a parametric curve, so we got the closed brackets. Inside of there, we got our x component, our y component, and then our z component. We're going to let u play the role of theta up here, and we're going to let v play the role of z, because r is being fixed at 4, and therefore I'm letting u be going range from 0 to 2 pi, and v I just chose to range from -4 to 4. Axes equals normal is one option, and I used the view option on here just to make the graph come out how I wanted it to. All right, and what we're seeing is a cylinder, hence the name cylindrical coordinates. We see the cylinder. So if you fix r equals 4, what does that mean? It's all points that are a radial distance in the xy plane from the origin 4 units. So it's essentially you're taking a circle in the xy plane. We look down the z-axis, that's what you see is a circle in the xy plane, and then you slide that up and down the z-axis to obtain this cylinder. So that's what we get with a constant equation where r is equal to a fixed number. Now we're going to fix theta. All right, so the equation I'm going to graph below is theta being fixed at pi over 4. So if I want to get theta, I can do it. One way to do that, you can use the common symbols palette over on the other side. You can type the word theta in and then hit the exponent key, and I'm going to do pi. Again, if you type the exponent key and then get off of it, that's what I'm going to do next is theta being pi over 4. So now we're going to put up in these equations for x, y, and z, we're going to substitute theta being pi over 4, and then we'll let u or v play the role of r and z. So we're fixing one of the variables, either r theta or z, and we're letting the other ones be the parameters. So again, I chose z to be playing the, or v to be playing the role of z. This time we fixed theta to be pi over 4, and u's playing the role of r now. All right, here's the graph below. What do we see? It is all the points that are at a 45-degree angle from the x-axis. So you're talking about a plane. All right, plane coming off of the z-axis, half plane coming off the z-axis. All right, we said at the beginning of this, if you let z be fixed, so this time we're fixing z at 3 in this case. This graph is the equation z equals, graph of the equation in cylindrical coordinates where z is equal 3. Then what we're going to see there is we're putting in 3 for z, and z is the same as it is in rectangular. And now we've got r and theta to be the variables that vary, the parameters. So I'm letting u play the role of r and v play the role of theta, choosing some r and v ranges. And what we're seeing is, no surprise, a plane parallel to the xy plane at height 3. All right, so at height z equals 3. All right, and you look at these trace lines on here, and the reason you're seeing this polar grid is because that's how we've chosen u and v. All right, those trace lines correspond to the polar coordinates. All right, so that's for cylindrical. Now we're going to move on to spherical coordinates. Okay, and I've got the graphs down below. I'm going to show them, but I think the graphs I'm going to do, I'm just going to type them up here real quick. They are rho equals 4, so that's a sphere. We're going to find out what that is. It's going to be a sphere of radius 4. Theta is going to equal pi over 4. And then the other one I'm going to do is phi equals pi over 4 in the video. And again, we could make that show up as actual math symbols. But what we want to think about doing there is for rho equals 4, we're going to look at the x equation, right? The x conversion, the y conversion, and the z conversion for a point rho, theta, and phi into x, y, and z. And we're just going to substitute wherever we see rho, we're now going to put in a 4. And then we can let theta and phi vary here. So that's all I'm going to do, and we're going to do this in parametric form. So we're going to do plot 3D. We're going to put our ordered triple in. That's with the closed brackets. And inside of there, I've got my x component, my y component, and then my z component. And those are obtained exactly from our spherical conversion formulas just by fixing rho being 4 and letting u play the role of theta. And I have this backwards in how I typed it. I typed cosine first, sine second down here, and v playing the role of phi. So I'm letting u range from 0 to 2 pi, phi, which is v is playing the role of phi, from 0 to pi. And what we get is a very nice graph of the sphere of radius 4 here. All right, very nice picture for that. All right, so if you're looking at an equation where rho is equal constant for spherical coordinates, what are you talking about? You're talking about a sphere. Hopefully that makes good sense. When we say rho is equal 4, we're saying rho is the radial distance from the origin out to your point. We're looking at all the points that are exactly 4 units away from the origin, and that means we're talking about a sphere. So we should expect it to be a sphere. What are we going to get for the other two? All right, so for the other couple graphs we want to do, we're going to type in theta, fix theta to be pi over 4, wherever we see theta, and then we're going to let rho and phi vary. Okay. All right, so I've done that here. Sorry, let's scroll back up here. So again, we fix theta to be pi over 4. We're letting u and v play the role of, in this case, rho and phi, respectively. So u's playing the role of rho, and v's playing the role of phi. And this is the graph we end up getting here. It's the same as it was in cylindrical. It's a half plane coming off the z-axis. What's different is, and I want to just emphasize this in OneNote to be able to draw on it a little bit, what are we doing here? We're first thinking about, all right, theta is fixed at pi over 4. Now, let's suppose we fix phi to be this angle here. Now, phi is fixed at that angle. Rho can be any distance along that angle out from the origin. So that's why we see these angles going out from the origin. Is we're talking about different values for the component for the angle phi, and then rho can range to be any point along any distance along that angle to generate a point on that graph. Okay, going back to Maple, so that's what an equation looks like when theta is constant. So we're going to get a half plane coming off the z-axis. Now, what do we get when we fix phi? So now I'm fixing phi to be pi over 4. Wherever we see phi in the conversion formulas, we're inputting pi over 4. U's playing the role of rho again. This time v is going to play the role of theta. In this case, we get a cone. All right, a cone coming at the 45-degree angle down from the z-axis. All right, that's what the graph looks like. All right, now let's just draw on that a little bit again over here in OneNote. Why do we get that? The 45-degree angle is the angle from the z-axis to the cone. Now we're saying we're fixing that to be a 45-degree angle, and you can go out as far as you want along that angle, and then you can go as much as you want around. All right, so we're going to go around that, and we'll wrap around this side. So that's why we're seeing these lines coming down, and we're seeing the angles going around. One of them is representing rho varying, the other one is representing theta varying. All right, so in that video we talked about the parametric description and of a surface, and then also the constant equations in cylindrical and spherical coordinates.